So going to discuss on a current source inverter. In the current source inverter, you are using a current source instead of a voltage source. And in order to convert the current source, we are having a voltage source which is connected in series with an inductor. And the output current is independent of the load. And the output voltage is dependent on the nature of the load and its impedance. And these are found applications in the speed control of AC motors, induction heating, VAR compensators, and synchronous motor starting. And a current source inverter does not require any feedback diode. And now we are going to discuss a single phase current source inverter with an ideal switches. So here what you see here is nothing but a current source, and then you need say is a current source inverter, and then you are having your load. So this system is having 4 thyristors T1, T2, T3 and T4. And the source is consisting of an EMF source which is connected in series with a large inductance. So it will maintain a constant current at the input terminals of the current source inverter. So when T1 and T2 are on, the current will be flowing from the load from this point to T1, then the load, then T2 and back to the supply. And when T3 and T4 are on, it will be moving from T3 to the load in the reverse direction, then T4 and then back to the load. So therefore you can see it when T1 and T2 are on, the current is plus I, and when T3 and T4 are on, the current is minus I, because the current is reversing its direction. Earlier the current flow was like this, and when T3 and T4 are on, the current flow will be upward. So you will be getting an alternating current at the output. So it's a square wave and the amplitude is equal to the DC input current. Now just assume that your load is having a capacitor. Therefore I can say that I0 is nothing but C into d V0 divided by dt. And now we have already plotted the waveform for I0, and we can see that I0 is constant. From the interval from 0 to t by 2, I0 is I and it is a constant value. And the capacitance C is also a constant value. So I0 is constant, which is equal to C into d V0 by dt, and C is also constant. So that means dV by d0, that is nothing but the slope of your output voltage, should always be the same. So with that, you can draw the basic waveform of how the load voltage will be looking like. So that is how we have drawn the output voltage V0 with a constant slope like this. And when it is reversing its direction, I0 has gone to the negative, and therefore with the same slope but at a negative direction, so a negative slope will be coming over here for V0. So that is happening when T3 and T4 are on. Now you need to plot the input voltage Vin. So this is the terminal at which you are finding out the Vin. And we have seen that the output voltage V0, it changes depending upon the direction of the current. But Vin is always the constant. So therefore, basically you can say that the Vin voltage can be drawn from the V0 voltage, and therefore V0 will be of the same slope of V0. And here also, since Vin is not changing its direction, Vin will be remaining like this when compared to V0, because V0 has reversed its direction, but Vin direction will not change because Vin is measured across this plus and minus terminals. But the V0 whatever which is measured over here is changing because the current is reversing its direction, because the current was flowing when T1 and T2 are on in this direction, and when T3 and T4 are on, it is going in the opposite direction. So you can also see that the frequency is twice the frequency of the output voltage waveform. That is, the input voltage waveform has a frequency of 2 times that of the output voltage. And in a practical inverter, the load current waveform will not be a square wave, and there will be a rise and fall in the current depending upon the value of the various components which is connected to the load. Now we are going to explain a single phase capacitor commutated current source inverter with a resistive load. So here you are using a capacitor, and the function of this capacitor is to commutate the thyristors. So here we are having 4 thyristors T1, T2, T3 and T4. So when T1 and T2 are turned on at this instant omega t equal to 0, then the current will be flowing as denoted in this case. That is, from the current source, it goes to the point A, which is equivalent over here, and then through the resistor and through the capacitor to the point B, and then back to the supply. Like this it is going. So during that time, the capacitor is storing energy. So before omega t equals to, so before this instant is 0, the capacitor was charged to a negative voltage. So it was minus and plus. That is a positive value over the capacitor plate on the right hand side, and the negative value over the left hand side portion of your capacitor. So when T1 and T2 are triggered on at this instant t equal to 0, then this negative voltage over the left plate of the capacitor is going to the thyristor T4, and this positive voltage is going to the thyristor T3. So effectively T3 and T4 are commutated by the capacitor voltage minus V1, which is coming across the capacitor. Therefore the current will start flowing, and you will be having the IAC will be like this for 0 less than t less than t by 2. And at t by 2, what I am trying to do is that I am going to turn on the thyristor T3 and T4. So while turning on T3 and T4, we will see what is happening to the thyristor T1 and T2. So during the period of 0 less than t by 2, the capacitor started charging from minus V1 to plus V1. So that is, the plate over the left hand side has become positive, and on the right hand side has become negative. Now this positive voltage is going to the thyristor T1, and this negative voltage is going to the thyristor T2. So this is going to the cathode and this is going to the anode, and therefore it is going to reverse bias, and when T3 and T4 is triggered on, then the current is taken over by the thyristor T3 and T4, which is going to commutate the thyristor T1 and T2. So that is going to happen at the instant from T2 to T. So during that time, the thyristor T3 and T4 will be conducting. So T3 and T4 will be conducting, and then the current will be flowing like this, and then back to the supply. And here whatever which is marked the direction is nothing but the conventional direction which you have marked in the reference figure. So that is just to indicate the actual marked direction of the current. So the current is actually getting reversed. Therefore effectively we can say that the use of this capacitor C is to commutate the thyristors T1 or T2 or T3 and T4. So from 0 less than t by 2, you are trying to commutate the thyristor T3 and T4 using the capacitor, because this plus value is going to T3 and this negative value is going to T4. And during this time of 0 less than t by 2, what happens is that the capacitor is again charging. So therefore at the end of T2, this point will become plus and this point will become minus, and that is being shown over here, which is helping in commutating the thyristor T1 and T2 at the instant of omega t is equal to t by 2. Now we will see the waveforms across the output voltage across the capacitor and also the capacitor current in the next lecture. Thank you.